Good morning, students. Chapter 4, Moving Charges and Magnetism. Yes, today's topic is torque on rectangular current loop in uniform magnetic field. Yes, it is one important topic. In this topic, we will consider two cases. First, what is titled? Torque on rectangular current loop in uniform magnetic field. Case 1. When loop is placed such that the uniform magnetic field is in plane of loop. Now, what is meaning by this? See, here it is. One magnetic pole, north. Magnetic south pole. Clear about this? So yes, due to this uniform magnetic field, is from south to north, sorry, north to south, okay, in this region, uniform magnetic field, that is uniform magnetic field B, it is in this direction. Clear about this? Okay. Now, when loop is placed such that the uniform magnetic field is in plane of loop, what is meaning of this? See, if it is rectangular loop, okay, then loop is placed such that the uniform magnetic field is in plane of loop, like this. Clear about this? When loop is placed like this, parallel to magnetic field. So four sides, rectangular loop, so four sides, 1, 2, 3 and 4, they are like this. Clear about this? Okay. Now, how to draw this loop? See, it is loop. Okay. Now let this loop is named P, Q, R, U. P, Q, R, U. Why R? S because it is from south. Okay. Just you can also write here it is S. So it is P, Q, R, S. We have one rectangular loop P, Q, R, S. Let this side is A and this side is F. Clear about this? Again, let when loop is placed, torque acting on rectangular current loop means like current is flowing. So that current flowing is I in this direction. So in this loop current is flowing I. In this loop current flowing is I. In this loop current flowing is I. Clear about this? Okay. So yes, see this title. When loop is placed such that the uniform magnetic field is in plane of loop. Clear about this? Okay. Yes, we have to find torque. What is torque? Torque is equal to force into perpendicular distance. So obviously, first of all, we have to find force. See, here, system is one rectangular loop. Rectangular loop means having four sides. So yes, first of all, we will find force acting on each and every section. What is force acting on PQ, QR, RS and SP? Clear about this? Okay, in magnetic field. Because we can consider this as current element. Current flowing is I and side is A. Yes or no? Yes, it is. So see, here, situation is as shown in figure. Now, see, force acting on wire PQ. Force acting on wire PQ. Force acting on wire PQ. Okay, let it is F PQ is equal to, what is equation of force? See if you remember, F is equal to IDL cross B. F is equal to, it is IDL cross B. Any doubt? Sure, F is equal to, it is yes, IDL cross B. Okay, so yes, here how to write? On this wire PQ, current flowing is I, side is A, so I can write like this. It is IA cross B. Now see, from figure it is clear. Magnetic field B and current I, magnetic field B and current I, they are in same direction. They are in same direction. They are in same direction. Yes or no? Yes, it is. So yes, if I find its magnitude FPQ is equal to IAB sine 0 and is equal to it is 0. Clear about this? Okay, now I will take this opposite wire. I will take this opposite wire. See, force acting on wire RS. Wire RS. Okay, so for wire RS, how to write equation? Yes, it is again F RS is equal to IA cross B. Clear about this? Current flowing is I, side is again A, and magnetic field. Now current I is in this direction, magnetic field is in this direction. What is angle between them? 180. Then yes, FRS is equal to I AB sine 180, and sine 180 is again 0. Okay, so yes, force acting on these two wires is 0. So see, from this you can say when wires are parallel to magnetic field, force acting on them is 0. Clear about this? Clear about this? Okay. Now force acting on wire QR. Force acting on wire QR. How to write equation? See, FQR is equal to current flowing I, length is L, so I can write it as IL cross B. Now FQR is equal to, see, current is flowing in this direction, I, magnetic field is in this direction. What is angle between them? 90. So it is ILB sine 90. And what is value of sine 90? Yes, it is 1. So it is ILB direction. What about direction? See, this is easy. IL cross B. Here it is. IL cross B. Clear about this? IL cross B. So thumb is going perpendicular inside. Inside means cross. Inside means cross. So here FQR is acting perpendicular inside. FQR is acting perpendicular inside. Clear about this? Clear about this? Any doubt? Okay, sure. So yes, what is force acting on it? What is force acting on it? Okay, now see, FQR is equal to FB sine 90, sine 90 is equal to this one, so I have it perpendicular inside. Similarly, on this wire at this point, at its center of mass, this force is acting perpendicular inside like this. Clear? Now, force acting on wire SP, force acting on wire SP, force acting on wire SP. Again, FSP is equal, it is IL cross B. It is IL cross B. So FSP is equal to ILB sine. See, angle between them. Yes, here it is. Here it is magnetic field and current is in downward direction. So what is angle between them? Yes, it is sine 90, and sine 90 is equal to, again it is 1. So it is equal to, it is again ILB. But what is direction? See now, I is in downward direction. Magnetic field is in this direction. So this thumb is perpendicular outside. This thumb is perpendicular outside. So yes, force acting on this wire is perpendicular outside. Okay. Yes, it is perpendicular outside. Clear about this? Clear about this? Okay. So see, FQR and FSP on both wires, forces are acting of equal magnitude and opposite direction. So what is resultant force? Force on wire PQ 0, force on wire RS 0, force on QR and SP, they are of equal magnitude and opposite direction. So resultant of them is 0. So first conclusion of this theory, resultant force acting on loop is 0. Resultant force acting on loop is is 0. Resultant force acting on loop is 0. Clear about this? Remember chapter number 1. When electric dipole is placed in uniform electric field, what is total force acting on it? 0. What is total force acting on it? 0. Similarly, when current carrying loop is placed in uniform magnetic field, what is total force acting on it? 0. But see, these two forces are of equal magnitude in opposite direction. How direction? See, we will think about this direction. See, here it is. On this wire, magnetic force is acting in perpendicular inside, and on this wire it is outside. Okay, this side force is acting inside, and about this point force is acting outside. Clear about this? These two forces are in opposite direction. These two forces are in opposite direction, equal magnitude. Yes, you remember one topic, two forces of equal magnitude, opposite direction, and when they are not collinear, they will form a couple. They will form a couple. On this wire, force is acting outside. On this wire, force is acting inside. So yes or no? These two forces are not collinear. So they will form a couple. They will form a couple. And due to that, see, it will perform rotational motion like this. It will perform rotational motion like this. Clear about this? On this side, outside. On this wire, inside. So due to that, it will perform rotational motion. Clear about this? And yes, the rotational motion is due to torque. Rotational motion is due to torque. So here, how to write? Here, F, QR and F, SP have equal magnitude, opposite direction, and not collinear, therefore they forms a couple. They produce a couple, and due to couple, torque is acting, and due to couple, torque is produced. Clear about this? And it will perform rotational motion. So question is, what is equation of torque? Remember equation of torque in case of dipole. Torque is equal to magnitude of any one force, because they both are equal, into most important thing, perpendicular distance between two forces. Now how to find perpendicular distance between two forces? One force outside, one force inside. So what is distance between them? Obviously this side. Yes, same figure. Here this force is perpendicular inside, this force is perpendicular outside. So what is distance between them? Yes, it is A. Clear about this? So see, magnitude of any one force, ILB, yes, it is same. Then it is ILB. What is perpendicular distance between them? Yes, it is A. Clear about this? So yes, I can write this as ILAB. Yes or no? Now L into A. See, A and L. What is area of rectangle? A into L. A into L. What is area of triangle? Yes, it is AL. So how to write this equation? Yes, I can write this equation as IAB. Tau is equal to, it is IAB, where I is current flowing from rectangular loop, A area of rectangular loop, and B is magnetic field. Now what about area vector? Yes students, you know area vector is always perpendicular outside. This loop is like this, so its area vector is perpendicular outside. Its area vector is perpendicular outside. Area vector is perpendicular outside. So in this case, area vector is perpendicular to magnetic field. Yes or no? Magnetic field is in this direction and area vector is perpendicular outside. So A and B, they are perpendicular to each other. So remember, when title is when loop is placed such that the uniform magnetic field is in plane of loop, or area vector is perpendicular to magnetic field. Area vector is perpendicular to magnetic field. In this case, dot is equal to it is IAB. Dot is equal to it is IAB. Clear about this? Now, second case, case 2. In this case, we have assumed this rectangular loop is parallel to magnetic field like this. Yes, it is easiest case. It is easiest case. Again, what is case number 1? This rectangular loop is parallel to magnetic field. But if this rectangular loop is not parallel to magnetic field, it is at some angle, then what happens? Then can we use this equation? No, we cannot use this equation. For this case, we have to obtain different equation. That is case 2. When loop is not in plane of magnetic field. When loop is not in plane of magnetic field. Yes, it is general theory. It is general equation. In that equation, if I will put some value, I will get this thing. Clear about this? What is method? Magnetic field, one rectangular loop, 4 wires. First of all, find forces on each wire, 1, 2, 3 and 4. From this, you can make or you can write some statements. Clear about this? So yes, we have to repeat this method for case number 2. Okay. Now case 2, when the plane of loop is not along the magnetic field but makes an angle with it. So see, we will draw figure. Here it is. Magnetic north pole, south pole. Okay, uniform magnetic field. Uniform magnetic field in this direction. Okay, uniform magnetic field in this direction. Clear about this? Now loop is placed like this. Loop is placed like this at some angle. At some angle. Okay, let this angle made is theta. Okay, so that loop is made at angle theta. Then what happens? See here. I can draw this loop like this. Sorry, I can draw this loop like this. Okay, it is P, Q, R, and here it is S. Yes, this side it is A, this side it is, sorry, it is L. Current flowing from this it is also I. Clear about this? So same situation. Just we have placed this loop at some angle. At some angle. What is method? Again, we have to find force acting on each and every. Okay. Now see, as this plane is placed like this, its area vector is perpendicular in this direction. So now this area vector and magnetic field, they are not perpendicular to each other, but they have some angle. Clear about this? So I am assuming that angle between area vector A and magnetic field B is theta. What is method? Find force acting on each and every wire. Okay, force acting on wire P. Force acting on wire P. FPQ is equal to current flowing is I, length is A, magnetic field is B. Yes or no? Yes, it is. Yes or no? Yes, it is. Okay, so yes, see here, this loop is like this. Current is flowing in this direction. Magnetic field, it is in this direction. Clear about this? Clear about this? Yes or no? Clear? Current flowing, it is in this direction. Magnetic field, it is in this direction. Okay, then how to find direction? How to find direction? See, I will place like this. Okay, this loop is like this. From this wire PQ. From this wire PQ. Okay, current is flowing in this direction. Current is flowing in this direction and magnetic field is in this direction. Current in this direction, magnetic field in this direction. So force is acting in downward direction. See in figure, current in this direction, magnetic field towards this. So force is acting in downward direction. Yes or no? Force is acting in downward direction. Now force will not become zero directly because now this I and B, they are not in same direction. They are not in same direction. So yes, force acting on wire PQ. Force acting on wire PQ. F PQ is equal to IA cross B. It is in vertically. It is in vertically downward direction. Clear about this? So yes, force acting on this wire PQ on its center of mass, it is in this direction. It is F PQ. Clear about this? Clear about this? Now for force acting on wire, opposite wire, take opposite wire RS on wire RS. F PQ. F PQ. Yes, current is same, sign is same, magnetic field is also same. So yes, magnetic field become same. What about the direction? What about direction? See here, from this wire, current is flowing in this direction. Magnetic field is in this direction. So wrap fingers like this. Thumb is going upward. Current is flowing in this direction. Magnetic field in this direction. Thumb is going upward. So yes, force acting on this is vertically. It is vertically upward direction. Means on its center of mass. It is in this direction. It is F RS. It is F RS. Clear about this? Now see, here it is. F PQ and F RS. They both have equal magnitude but direction opposite. And yes, they are collinear. They are collinear. Yes or no? So yes, the resultant force is zero. And also, torque is not produced due to them. Clear about this? Then how to write? See, F PQ and F RS and F RS. They both have equal magnitude. They both have equal magnitude. Opposite direction. Opposite direction. Okay, and they are collinear. So their resultant sigma F is equal to 0. And yes, due to them, sigma tau is also 0. So yes, due to this two wire, resultant force is 0. Due to this two wire, torque is not produced. Now, remaining two wires. Okay, see, remaining two wires. For wire QR, force acting on wire QR, force acting on wire QR. Okay, it is F QR is equal to IL cross B. IL cross B. Clear about this? Okay. How to find its magnitude? F QR is equal to ILB. What about angle? See, here it is. This loop is like this. Yes or no? Current is flowing in vertically upward direction, while magnetic field is in horizontal direction. What is angle between vertical and horizontal? 90. Again, current is flowing in vertical direction, magnetic field is horizontal. So what is angle between them? It is sine 90. Clear about this? Sine 90 is equal to 1. So FQR is equal to ILB. What about direction? What about direction? See, current is flowing in upward direction. Magnetic field is in this direction. So thumb is perpendicular inside, and perpendicular inside means you know its symbol. perpendicular inside. Okay, force acting on this wire, it is perpendicular inside. Clear about this? Okay, now what is force acting on wire SP? Force acting on wire SP, force acting on wire SP, FSP is equal to current flowing I, length L, magnetic field, yes it is B, its magnitude FSP is equal to ILB sine. See, current is flowing in this vertical direction, magnetic field is horizontal. What is angle between vertical and horizontal? Yes, it is 90, and sine 90 is equal to 1. So FSP is equal to, it is ILB direction. Current is flowing in downward direction. Magnetic field in this direction. So thumb outside. Again, current is flowing in downward direction. Magnetic field in this direction. So thumb is perpendicular outside. So yes, force acting on this wire is perpendicular outside. Okay. Yes, it is perpendicular outside. Clear about this? Okay. Now, FPQ, FRS. Total force 0. No torque due to them. But due to force FQR and FSP, see, their magnitudes are equal. Direction is opposite, but they are not collinear. Yes, they are not collinear. Yes, this plane is like this. Yes or no? On this side, force is acting towards you. On this side, force is acting towards me. Yes, they are not collinear. So they will form a couple, and due to that, torque is acting. Due to that, torque is acting. So see how to write. I will write like this. Okay. Okay. FQR. Yes, I just FQR and FSP. They both have equal magnitude. Equal magnitude. They both have opposite direction. Yes, opposite direction. Opposite direction. And they are not collinear. Not collinear. So yes, total force becomes 0. Sigma F is equal to 0. But sigma tau is not 0. But sigma tau is not 0. Remember, what is difference between these two cases? Here FQR and FSP, they have equal magnitude, opposite direction, but they are not collinear. So yes, resultant force is 0, but resultant torque is not 0. Clear about this? Yes, resultant torque is not 0. Then what is torque? Yes, we have to find equation of torque. See, torque. Okay, torque is produced. Torque is produced. Okay, so what is equation of torque? Torque, yes, again, what is equation of torque? Torque is equal to force, magnitude of any one force, into perpendicular distance, into perpendicular distance between two forces. Between two forces. Now, see, at first sight, it seems, yes, distance between two forces is similar to first case, it is A, not A. See, here it is. Here it is. First of all, plane is like this. This side, forces acting towards you. This side, forces acting towards me. Then what is distance between them? A. Now, if I rotate like this, okay, then see, if force is acting in this direction and this force is acting in this direction, force distance between them decreases. As I rotate this plane, distance between two forces, perpendicular distance between two forces decreases. In this case, distance between them becomes 0. Clear about this? Okay. So what is meaning of perpendicular distance? Initially force is in this direction. It is in this direction. Then distance between them is this A. Distance between them is A. If I rotate plane like this, see, like this. My finger is in this direction, this finger it is in this direction. So yes, distance between them is not A. Distance between them is not A. Then how to find distance? If I see this same thing from top side, means get top view, means top view, then I can draw figure like this. See carefully, here it is. As that plane is slant, it is nothing but this wire SR, but it is enlarged. We have zoomed it. Okay, it is psi SR. Okay, on this side, force is acting in upward direction, means in this inside, means in this direction. It is force FQR, and yes, it is force FSP. Clear about this? Clear about this? Perpendicular distance means what? See, if I draw line of action of this force, perpendicular distance means that distance makes angle 90 with each and every force. Is this angle 90? No. Is this angle 90? No. So it is A. It is not perpendicular distance. What is meaning of perpendicular distance? See, if I draw one line like this, clear? See, it makes angle 90. See, it makes angle 90. Then this is called perpendicular distance between two forces. Yes, let it is named MN. Clear about this? Or yes, it is KN. For example, it is KN. So yes, perpendicular distance between two forces is KN. Now we have to find KN. Let this point is O. Okay, clear about this? Now, magnetic field is in which direction? Magnetic field is in this direction. It is direction of magnetic field. Magnetic field is in this direction. Plane is placed slant. Yes or no? So what is angle between area vector and magnetic field? That area vector is perpendicular. See, it is plane, huh? It is plane. So area vector is perpendicular to it. Magnetic field, it is in this direction. See, parallel magnetic field is in this direction. I have assumed that angle between A and B is theta. So yes, this angle is theta. Clear about this? About figure? This plane. Area vector is always perpendicular to plane. It is plane. Area vector is always perpendicular to plane. So if this angle is theta, this angle becomes 90 minus theta. Clear? Clear about this? Okay. It is top view, means it is nothing but SR. And SR, you know that SR is equal to it is A. SR is equal to it is A. So if it is its midpoint, I can say it is A by 2. It is A by 2, and it is also A by 2. What I have to find? I have to find Kn. From figure you can say, sir, Kn is twice of On. So yes, I will find On. See how to find On in this triangle O and R. In this triangle, I want to find On. On is adjacent side of 90 minus theta. On is adjacent side of 90 minus theta, and this is hypotenuse. Then take cos theta. See, cos 90 minus theta. Adjacent side is On divided by hypotenuse is A by 2. Clear about this? Cos 90 minus theta means yes, it is sin theta. And if I take A by 2 this side, then A by 2 sin theta is equal to On. Clear about this? Now this On is equal to okay. On is equal to okay. So how to write Kn? How to write Kn? Kn is equal to 2 times On is equal to 2 times A by 2 sin theta. 2 cut means it is A sin theta. So what is perpendicular distance between two forces? A sin theta. Clear about this? Okay, so now how to write equation of torque? Like this. Torque tau is equal to force. What is force? ILB. So force is ILB. What is distance between them? A sin theta. Clear about this? So torque tau is equal to it is ILAB sin theta. Again, N into A means area of rectangle. So torque tau is equal to IAB sin theta. And yes, it is general equation. Torque tau is equal to IAB sin theta. But what is theta? Angle between A and B. Now remember first case. In first case, in that corner, okay, A perpendicular to B. A perpendicular to B means what is angle between them? 90. So if you put here sin 90, you will get tau is equal to I in B. So yes, if you know case 2, you can derive case 1 only in 2 steps. You can derive case 1 only in 2 steps. But as is given in your textbook, we have to derive both cases. Clear about this? But you have to remember this general equation. You have to remember this general equation. Clear about this? Now, last step. Okay, last step. Torque R is equal to IAB sin theta. Okay, here this IA, it is called magnetic moment. Here this IA is called magnetic moment. Is called magnetic moment. Okay, so how to write this equation? I can write this equation as torque tau is equal to IA is called magnetic moment, means it is MP sin theta. Is called MP sin theta. MD sin theta. Torque is vector quantity. Magnetic field is vector quantity. Magnetic moment is also vector quantity. What is direction of magnetic moment? Magnetic moment's direction is direction. How to find? See, here it is. Current is going in this direction, like this. So rect fingers in direction of current. Simple. Rect fingers in direction of current. This thumb indicates direction of magnetic moment. This thumb indicates direction of magnetic moment. Clear about this? Clear about this? So yes, this magnetic moment, magnetic field, and angle between them is theta. Angle between them is theta. So how to write this in vector form? Tau is equal to, it is M cross B. Tau is equal to, it is M cross B. Tau, magnetic moment into magnetic field. Remember chapter number 1, electric dipole in uniform electric field. Tau is equal to P cross E. P, electric dipole moment. E, electric field. Similar result we have obtained in case of magnetic field. Tau is equal to M cross B. Tau is equal to M cross B. Clear about this? Now in next lecture we will see in detail about this magnetic moment. Clear? So yes, it is one important theory. But understand which case is asked, case 1 or case 2. Clear about this? Watch videos regularly, write notes, solve your doubts, appear in an exam, and yes, do like, share and comment